So covariation refers to the relationship between two variables such that the presence or magnitude of one of those variables can be used to predict either the presence or magnitude of another variable. Now covariation can be either positive or negative. I suppose it could be zero or null, but that rarely happens. Just because numerically when you're measuring it, you'll always get some outcome. More often, instead of worrying so much about zero or non-zero, we just sort of look at classes of the degree or size. That applies more to correlations still. But nonetheless, covariations that are positive are just implying that both variables either increase or decrease together. So an example of that would be exercise and cardiovascular health, that the more people tend to exercise, the higher their cardiovascular health tends to be, and the less people exercise, the lower their cardiovascular health tends to be. Now, negative one would just be that as one variable increases, the other decreases, and vice versa. So here could be an example of, again, let's use exercise and stress. The more people tend to exercise, the less stressed they tend to be, and the less people exercise, the more stressed they tend to be. And so this just goes to show you that as one increases, the other decreases. Now, correlations, which oftentimes come up in a statistical class, correlations are just a standardized form of representing covariation. Technically, so long as you know the standard deviations of whatever it is, the variables that you're measuring, you can interconvert freely between covariations and correlations. Covariation oftentimes remains or takes into account the raw units and the distribution of those units, whereas correlations are all standardized, and thus you can actually compare them across different types of relationships. Now, why should we care about covariation? Well, on a general level, all human beings are just ultimately fundamentally geared towards detecting covariation, whether they want to or not. What I mean by this is that most humans are not only good at, but also continually looking for patterns in the world around them. And from an evolutionary point of view, that's very advantageous, because knowing what foods make you sick and what foods don't make you sick is very important. And ultimately, that is an exercise in covariation. What foods covary with sickness and which ones do not? And knowing that information is ultimately very good for a human being. Chances are most creatures also are like this, but we really are talking about human beings here. Okay, so all human beings ultimately are obsessed with this because we find patterns even when there are not patterns present, which we'll talk about in the next couple of slides, of that even though we're always doing this, humans are not really the best at it. Now, from a scientific standpoint, establishing covariation is really, really important because it is one of the fundamental requirements to make any type of causal claim. If you have not established a relationship or ultimately covariation, you cannot make causal claims. Now, just something to provoke thought here, I suppose. Many people have heard this sentence that gets thrown out all the time of correlation does not imply causation. And that is definitely true. Just because two things are related does not mean that they're causally linked together. One of the most common examples of this is that boating accidents, or the frequency of boating accidents, is related to the number of ice cream sales, such that the more ice cream sales there are, the more boating accidents, and the less boating accidents, the less ice cream sales. Now, they're correlated, but that doesn't mean they're causally linked. This is also talked about in regard to something called the third variable problem, which is oftentimes hidden third variables that we're not aware of. And so in this case, that third variable would be the time of year. In the summertime, more people go on boats and eat ice cream, which just leads to higher rates of both of those. And in the wintertime, people do less of both. Doesn't mean they're causally linked. But now, what about the inverse of this statement? Does causation imply correlation? You could take a minute here to be like, yes or no. And the answer would be yes, it must imply a correlation, because if one thing causes another, then those two things will ultimately have a relationship and they will tend to covary, because if X causes Y, then whenever X is present, then Y will also be present, leading to this type of relationship. So just because we're always doing this, and even though we have developed tools to allow us to get around some of the limits that we have on detecting covariation, even when trained, people still tend to make a lot of mistakes. especially one of the most common that is found is that when you are trained, you're often trained in a particular domain. Like let's say a chemist is taught to deal with probabilities and covariation in their field of study, but they won't necessarily then apply that same training to other fields of their life, like when they go to a doctor and need to understand about medical test efficacy or something like that. And this is just true for human beings in general. And to make it worse, the majority of us don't have any type of formal training in probability or empirical method, and so we are already kind of at a disadvantage in terms to being accurate in detecting covariation. Three things that we'll talk about in regard to this is one, limited and biased samples. That's here on this page. The other two will be confirmation bias and base rate neglect, which will just come up in a couple slides. So there's an old saying that I got a lot of times, even though I think lots of people have heard this, but we got this in terms of electrophysiology when we were reading brain waves, but garbage in equals garbage out. And the idea here was that if your recordings were really shitty and really messy, no matter how good your study, the data is also going to be really messy, because if everything you're putting into it is messy, leading to messy data, then all of your conclusions are also going to be messy because you're making your conclusions on ultimately noisy data, which is not the greatest way to make conclusions. So even if our ability to make conclusions was totally accurate, we just never even made any mistakes, which is definitely not the case, our conclusions would still only be as good as the data that came in. And so when it comes to detecting covariation, humans oftentimes don't look at all the possible situations where something could be occurring. For example, if I think to myself, chicken noodle soup is a great way to help me get over the flu, and every time I have a flu, I make some chicken noodle soup and I eat that chicken noodle soup, and then in a couple days I feel better. And so I say something like, me eating chicken noodle soup is related to my getting better, and I think eating chicken noodle soup makes me get better. Now, sure, that might be true, but ultimately one cannot make the overarching claim that chicken noodle soup makes people better from the flu because we don't know the general range of experiences. I only know about it for myself, especially if I'm not recording this in an empirical sense. I don't know all the people who didn't eat chicken noodle soup and got better, or all the people who had chicken noodle soup and did not get better. And because those all come into play when trying to figure out what the relationship actually is between chicken noodle soup and getting better from the flu, we're oftentimes not looking at the entire range of experiences that are possible, and so that will limit the conclusions that we can make about those relationships. These are related to, well, egocentrism, right? We tend to look at the world from our own perspective, and oftentimes we use that as the metric to judge all things, even though in many cases that's not necessarily an accurate way of going about it. And more formally, a lot of times that's called the present bias, that we tend to be very focused on what is available and in front of us, and we tend to ignore what is not available and not in front of us. So I will pay much more attention to all the times I got better when I had chicken noodle soup and got or recovered from the flu, but I will tend to ignore other people's experiences, and I will tend to ignore my own experiences where I didn't eat chicken noodle soup and got better, and I will tend to ignore the times where I ate chicken noodle soup and didn't get better. Right? We tend to focus on majority of the time those things that are just immediately present for us and not the things that are not. This is again just one of the fundamental biases that human beings tend to have. Now, confirmation bias is related to this, and this refers to the phenomena where people tend to be much more sensitive towards evidence that confirms their beliefs than they are to evidence that challenges their beliefs. And you could replace the word sensitive with receptive if you wanted, that people are just more open to things that fit with their ideas of the world, and they are more resistant to things that challenge those beliefs. And this is, again, something that is seen across all of humanity. Now, what's crazy and relevant to this class specifically is that not only do you see this in behavioral data of how people operate and make conclusions, but even functional MRIs show us that brain activity is actually different regarding how one is dealing with one of these two different types of evidence, evidence that confirms our beliefs versus evidence that doesn't. Whenever we have discordant evidence or evidence that disagrees with our point of view, this actually causes increased activation compared to congruent evidence in our amygdalas, which are often associated with fear and salience, and a greater degree in the amygdala, and also less frontal cortex activity, which is oftentimes associated with abstract thought and complex reasoning. And so here what's thought to be going on is that one, the discordant information causes a degree of anxiety and fear. It just is a natural response, which tends to put human beings more into this fight or flight mode. I mean, it's not like a switch gets flipped and that's entirely what happens, but it's about the subtle biases that take place. And when one is in that anxious state, one is less likely able to truly internalize and think about novel material. That then is related to this difference in frontal cortex activity, where a lot of that type of more abstract and complex reasoning is taught to take place. Something you could think that's related to this is when people drink alcohol. Alcohol preferentially inhibits frontal cortex cells over all other cells in the brain, which is kind of weird. Ultimately, all of them will get inebriated or depressed in some ways. And depressed, I mean in terms of like firing activity, not an emotional state. But so one of the reasons why people make so many dumb decisions when they're drunk is because of that sort of decrease in activity in the frontal cortex, and they're not able to maintain as many complex rules and thoughts. And most of society's rules are complex and abstract. And so this is why when you're drinking, those are oftentimes the first things to go out the window, and a lot of times why people will either get into fights or act in ways that they wouldn't necessarily have acted before. Another interesting phenomena that comes up in regard to confirmation bias is that let's say the majority of people tend to believe that they are less susceptible to this than the average person. Right? Most people think that, yeah, that's true, people are preferential in how they look at evidence in the news and that kind of stuff, but I'm not one of those people. And ultimately, most people think like this. And again, this is not that people are stupid or something. This is just part of how we look at the world. And at the end of the day, you have perfect access to your memories and your thought processes, but you do not have access to all the mechanical and fundamental little bits and pieces that are going on underneath the surface. And since we only have our experience, and our experience seems perfectly authentic to us, we don't really know when this type of thing is happening and when it's not, because ultimately it's an automatic process that's taking place underneath our conscious awareness. And so human beings don't actually have access to this. This is, again, one of the reasons why we developed the scientific method, is because it is a way of quantifying information in the world, and it tries to reduce our own biases that we would bring to the table by trying to be objective in recording that data, and also getting around that present bias that I talked about on the previous slide. Finally, we have something called base rate neglect. So base rates just refer to how often or what proportion of a given population shows some particular instance, trait, or quality. So an example of that would be about 63 out of every 100 households in the United States of America own a dog. Right? This is not saying that if you were to take every 100 households that always 63 of them would own dogs, but if you were to go across all of the United States of America and chop it up into 100 batch households, on average about 63 of them will have dogs. Now, this information is really quite vital to make accurate estimations about covariation, because remember how I talked about, if you're only using information that's immediately available to you to make conclusions about covariation, ultimately it'll be limited by the data that is coming in. And a lot of times we don't look at what the general rates are that things happen in the world, because that's an important part of making estimates about covariation. And we ultimately tend to overlook this a lot, which is why this is called base rate neglect. Now, this gets compounded or becomes even worse when we are not only given base rate information, but we are given information in terms of a description or narrative about the people or categories that this base rate applies to. What I mean by this, well, actually I have a good example of this on the next slide. So making this even worse is that we tend to ignore base rates and look at trait qualities or descriptions, and then a lot of times in the world we just don't have access to accurate base rate information. From a scientific point of view, it is already lacking because it is difficult to measure entire populations. And then from a non-scientific standpoint, most of us don't even know what base rates are, let alone where to find them or how to estimate them accurately. So an example of base rate neglect is, consider a person named Sally. Sally likes to go listen to classical music. Sally also likes to read about history and very much enjoys going to museums on the weekends. So knowing this about Sally, determine which of these following statements is more likely to be true. So either Sally is a farmer or Sally is a trumpet player for a major orchestra. Now, of course, you're probably sensing that there is a trick here because we just talked about base rates, and well, you'd be right, I guess. But here, really what I want you to think about is which of the two options you sort of intuitively lean towards. The majority of people are going to select B, where Sally is a trumpet player in a major orchestra, as opposed to Sally is a farmer. And a lot of this is going to happen because of our preconceived notions of farmers and trumpet players. So someone who likes to listen to classical music and go to museums is more, it fits with our ideas and stereotypes of someone who plays trumpet versus someone who's a farmer. We often don't necessarily associate farmers with liking classical music. Gender plays a role here too, because we tend to perceive farmers as more masculine than more feminine, and oftentimes that will also bias our decisions. That being said, in this case, we are ignoring the rates at which farmers and trumpet players in major orchestras occur in the United States of America, let's say. And by doing so, we're not actually going to make accurate estimations of which is true, because that original statement about her liking classical music, reading history, and going to museums doesn't actually give us any information about whether Sally is a farmer or a trumpet player. So there are about 2.1, 2.2 million farmers in the United States. There are only about 4,000 trumpet players in major orchestras across the entirety of the US. So here you can see that there's an order of magnitude more farmers than trumpet players. And so just on that basis alone, it should be more likely that Sally is a farmer versus Sally is a trumpet player, because at the end of the day, we don't exactly know based on that description. And so our best bet would be, what are the numbers of people that are in the entire population that satisfy these two criteria, and whichever one they're more of, that's more likely to be what Sally is, right? So in this case, for being farmers, that would be about 2 out of every 300 people is a farmer, because there's about 2 million farmers. There are about 320 million people in the United States, so that's like 2 over 320 would be sort of the rate at which someone could be a farmer. Whereas for the trumpet players, that is only 4,000 for every 330 million people, which is way less than 2 million out of that. And so again, likelihood being Sally is a farmer. And so this is just to illustrate that in many cases, we will automatically make judgments based on our stereotypes that are driven by the descriptive information that we get, and we will often overlook that more fundamental base rate information. Again, I cannot reiterate enough, this has nothing to do with humans being stupid. This is all about the way in which human beings tend to look at the world. We organize the world in a narrative structure of causal chains. It's just how we make sense of the world. And just because we make sense of it in a particular way, and just because that can be adaptive, does not necessarily mean that that is the way the entire world works. An example of this from physics, you could say, is that we see the world in our colors, but as far as the light that we use to see, it only qualifies a small spectrum of all that is available. And not everything sees the same spectrum as us. For example, there are some creatures that can see much farther into ultraviolet light than we can. And it changes ultimately the way that the world exists. So just because our perspective might be adaptive doesn't necessarily mean that that's the way the world works. Bringing this back to covariation, just because we think certain types of people are a certain way, or certain types of things are related to our behaviors, doesn't necessarily mean that they actually are.